Hello everyone, welcome to my presentation on reducing logic locking key leakage through the scan chain. My name is Kyle Dreitis. I'm an assistant professor at Villanova University. This work was done while I was at Drexel University as a PhD student with my advisor, Dr. Ioannis Savidis. An outline of the talk today will first start off with a trade-off between testing and security, and look at a brief overview of scan chain operation and hardware security. Then we'll look at some prior work on obfuscating the scan chain, and then look at how to expand the threat models for scan chain security, both with a logical formulation and then adding frequency-dependent scan chain security, and then we'll offer some conclusions. So the goals for integrated circuit testing first include checking the circuit functionality, so analyzing logical, timing, or reliability problems or concerns with the circuit, and validating that the circuit is operating as intended. So validating there's no stuck-at faults or reliability problems with regards to process voltage or temperatures. Now, large integrated circuit designs pose some challenges to validating the IC because they have an internal state space. So the primary outputs not only depends on the primary inputs, but the internal state of the IC. And the lack of controllability or observability of this internal state limits the ability to fully test the IC. So the scan chain resolves some of the observability and controllability issues of the internal register state by turning in the registers into a shift register functionality. So that will, instead of taking the data input from the combinational logic path into the flip-flops, when scan enable is high, it will take in the scan input for the SI input shown on the left. Now, typically the scan frequency is lower than the at speed frequency due to temperature and power concerns of the high switching activity in test mode. So you can see based on the waveform on the left that the scan data is shifted in, and then scan mode is disabled to allow for capture of an at-speed test pattern, and then scan mode is re-enabled to capture the data within the registers and observe their outputs. I'll take a brief look into background and hardware security. So the hardware supply chain has shifted from once vertical supply chain to a horizontal supply chain with a lot of globalization. So if we look on the right here, from project design to final assembly, there's a lot of different stops throughout the world, and each of those stops could potentially be an untrusted third party that can cause a security concern. So first and foremost, this caused monetary costs. So there's an estimated $7.5 billion lost to counterfeits in 2014. And maybe more importantly, there's security costs. So we've already seen backdoors in military ICs and have seen counterfeit ICs discovered in US Navy planes. So on the right here, we have an example of a counterfeit where you can barely tell the difference between the top and the bottom IC package. Maybe some small differences in packaging marks. And you can only really tell the difference through the X-ray inspection of the device. But even if you don't have a ground reference for the two devices, it's difficult to tell which device is correct. So that creates an inherent trade-off between testability and security. So reducing observable information would make it more secure because an adversary would have less information. For example, if you eliminate the scan chain data, it becomes more difficult to execute SAT-based attack because now the adversary has to search through different circuit states. So unrolling the circuit is the only way to create a combinational model of the circuit. Whereas testability would then be decreased, though, because you have less observability control within the IC itself. So the question then is, how can security be increased without modifying the testability of the IC? So if we look at prior work on obfuscating the scan chain, most of the prior work focuses on encrypting the data outputted from the scan chain, so that only an authorized party correctly utilizes the scan chain. However, the actual obfuscation does not target the combinational logic between registers in the typical case, which means that you have to add extra logic locking to secure the combinational logic. In addition, you see attacks such as the scan-sat attack, which can reformulate the scan chain logic as a combinational circuit to use multiple input-output patterns to attack the scan chain logic locking key. So other work to remedy the issue of the scan-sat-based attack uses a dynamically obfuscated scan chain. So here in LFSR, we'll actually update the key for each time period, and then the scan-sat and sat-based attacks will have difficulty determining the key because they usually try to determine a static key. So as the key updates, the solution to the SAT solver no longer applies. So really the question is, we've seen that you can secure the scan chain contents themselves, but we really want a larger threat model to be encompassed. So first, if we add reverse engineering as a threat model, we have to consider the combinational logic between the register paths. And if we want to use the current work, we'd have to add additional logic locking. So you'd have increased power, performance, and area overhead. Additionally, the encryption or use of the scan chain for only a trusted entity might provide a larger burden on an IC design firm, because only trusted parties can test and validate inputs to the IC. So if we want to add the ability for an untrusted entity to test given patterns, we have to change the formulation of scan chain security as well. So first we'll look at a logical formulation of our work on how we can expand the threat model. So here we have this key gate where key 0 is applied to an XOR gate within the combinational logic of the IC design. And here the test signal will actually switch out from the key being applied to a test signal being applied. So now whenever we're in scan chain mode, there's no key data applied to the circuit. It's all based on a test signal. So this means that the adversary no longer has access to reverse engineering attacks because the combinational logic itself has been modified. And now also untrusted third parties are able to test input and output combinations without knowledge of the key. So any possible input-output combination can be tested, but there's no key applied to the design to have a ground truth of the Oracle IC. Additionally, we can look at ways to utilize the difference between the frequency of scan chain operation and functional operation. So to do that, we designed a charge accumulation-based circuit. So in this case, it'll accumulate charge when the clock is equal to 0 and discharge through the transistor N2 when clock is equal to 1. And then we can use this to detect attacks within the circuit and ensure that scan mode is only active when operating at the intended scan mode frequency. And we can then also have a locality-based security where if someone's trying to insert a fault at a given location, these other charge accumulation circuits throughout the design will give a false reading and not allow scan mode to be entered. So if we look at a simulation of the circuit here, we can see that 100 megahertz test mode frequency outputs a logic 1 on the output of the charge accumulation circuit. But if we increase the frequency to 1 gigahertz, we see that the frequency actually outputs logic low after 3 cycles. So only in the test mode frequency do we see the logic output high, which would obfuscate the current key value or the control value applied to the charge accumulation circuit. So if we look at a case study for the ISCAS 89S27 benchmark circuit, we can see here that under nominal operation with an input of all logic zeros and to the scan mode input, and then an input to the circuit of G0 equals 1, G1 equals 0, G2 equals 1, and G3 equals 0, we see that register 1 is a logic value 1 after in the scan out port, and that registers 2 and 3 are logic 0 in the scan out port. So if we then insert a charge accumulation circuit at node X, we can see that even with the inputs, the same inputs of G0 equals 1, G1 equals 0, G2 equals 1, and G3 equals 0, that the R1 output is now logic 0. So we get a different functional response, and the key information has actually been concealed in scan mode and limited the observable oracle information. So to summarize the results here, the charge accumulation circuit has a low overhead and power performance and area. So we see that the circuit itself is about the same size as a 2-input NOR gate in 180 nanometer technology. It has a 9.2% overhead and area. Whereas overall, there's a 12.9% area overhead for the ISCAS 89S27 benchmark circuit. However, as you insert these circuits into a design that's considerably larger in nature itself, the overhead should shrink in area as well. So this provides some assurance that the IC is in test mode and scan mode, and that the key information is not being revealed. So it depends on more than one logical signal. It can reduce susceptibility to fault injection attacks because of that dispersion of locality of these charge accumulation circuits without the IC. So now if someone's trying to insert a fault like a focused ion beam at a specific location with the IC, the other charge accumulation circuits will read different values and tell the IC not to allow scan mode to be accessed. So in conclusion, there is an inherent trade-off between the goals of high testability and high security. So you have observability and controllability of the internal circuit state must be protected for security to be preserved. And you have previous scan chain security that was focusing on altering the scan chain output. So this only allows a trusted party with the key to decode the scan chain output, and it requires extra logic locking to secure the combinational logic under a reverse engineering threat model. So in this work, we develop a protection mechanism that removes access to the key during test and scan mode, both in a logical functionality approach and adding a frequency dependency that allows for an alteration of the key logic when scan mode is entered. So we see that the charge accumulation circuit has a 9.2% overhead and area when compared to a minimum size 2-input NOR gate, and a 12.9% area overall for the S27 ISCAS benchmark circuit. Thank you.